Let's talk about implicit differentiation. So when we have an equation like y equal to x squared plus 1, this defines y explicitly as a function of x. So when we say the word explicit, it's sort of like we're saying very clearly, very directly what y is equal to. So when you have a explicitly defined function, you can always write it in the form y equal to f of x, like this, okay? Now, let's take a look at a different equation, or a seemingly different equation, the equation y minus x squared equals to 1. In this case, this equation is not y equal to something. Now, there is a function buried in here. I hope you could see that we could just use algebra to solve this equation and get this first equation that we had. But when we write something like this, we say that it defines y implicitly as a function of x, okay? So there's really two ways of looking at the description of the function. One is explicitly and one is implicitly. And for us, a very key idea, especially when we're defining y implicitly as a function of x, is to know that the derivative of y is dy dx. And of course, this is our standard depiction of the derivative of y in Leibniz notation. All right. So when we are doing implicit differentiation, the derivative of the expression xy requires the product rule. Why does this require the product rule? Because we have two functions. One function is x and the other function is y. So when we look at our product rule, we could write it as sort of the f function is equal to just x and the g function is equal to y, right? So we know that when we use the product rule, the derivative of the product, the derivative of fg is equal to f prime g plus g prime f, right? So when I go ahead and apply the product rule to the expression xy, what am I going to get? Well, the derivative of x is just 1. I keep the second function, which is y, and I add what I get when I take the derivative of the second function. G prime is going to be dy dx, and I keep the first function f, so I just write the x there. So this is the result of applying the product rule to xy. Similarly, when I'm doing implicit differentiation and I want to calculate the derivative of the expression y over x, this is going to require the quotient rule. Now recall that the quotient rule says the derivative of a quotient of two functions is equal to the derivative of the top times the bottom function minus the derivative of the bottom function times the top function, all divided by the bottom squared, right? So when I go ahead and I calculate the derivative of y over x, the derivative of the top function is going to be dy dx. I keep the bottom function, which is x minus, I take the derivative of the bottom, which is 1, and I multiply by the top function, which was y, all divided by the bottom squared, which is x squared. When I'm doing implicit differentiation, the derivative of the expression y squared, this one requires the chain rule. So remember, the chain rule tells us how to find the derivative of a composition of two functions, f composed with g of x. And the way that worked was we took the derivative of the outside, we kept the inside function, and then we multiplied by the derivative of the inside function, right? So in this particular case, our outside function is x squared. So when I take the derivative of the outside, I'm going to get 2 times something. I got to keep the inside function, which is y squared, and then I got to multiply by the derivative of the inside, which is dy dx. So we have a general strategy for how to solve problems using implicit differentiation. And it's a multi-step procedure. The first thing we want to do is we want to take the derivative of both sides, take derivative of both sides with respect to x. This means that when I say with respect to x, we're saying x is the independent variable. So we treat y as a function of x, just like we did in the discussion up above. The second thing you want to do is you want to move everything involving dy dx to the left side of the equation. And move everything else to the right. All right. The third thing we want to do is you want to factor out dy dx. And then the last thing you want to do is you want to solve for dy dx by dividing. So we will definitely look at examples together in class. Before we wrap up this video, I want to emphasize another aspect of implicit differentiation with you. So let me draw a set of axes here, and let me have my curve over here be something that looks like this. So this curve right here is x squared plus y squared equal to 1, let's say. So I'll put a 1 there and a 1 here. Okay. And one thing that you'll notice is that this is not a function. It fails the vertical line test. But the important thing to notice is we can still talk about tangent lines, right? If I said, what's the tangent line to the curve at x equal to 1/2, maybe I should label that right here, 1/2 over here. Well, the issue is because this is not a function, because it fails the vertical line test, I don't know if you mean the point here, or I don't know if you mean the point here. So if you meant the point up here, then when we talk about our tangent line, the tangent line might look something like this, like that. But if you talk about down here, then the tangent line might look like this. So you need to specify, we need to specify the y value. Why do I bring this up? Well, when you are doing implicit differentiation, and then you calculate your dy dx, and we can look at this example in class together, what you're going to find is that your derivative has both x's and y's inside. And the reason for that is this situation over here. It's not enough just to give the x value. I need to give you the y value in order to know which one of these two I need the tangent line for. So many of our derivatives in this section will have both x's and y's in them. All right, everybody, we'll look at many examples in class together. Take care.